Cool. Pause this for.
Are we gonna go over the superposition analysis today?
Sure.
All right.
You couldn't follow my lecture on the YouTube? Well,
Yeah.
it's okay. You can only do so much in the absence of having me there to answer questions that come to mind. You know, it's only fair. But that was recorded for my daytime section of 50 students, and they're facing the same homework exercise. The solutions for that are right here. Here's the solutions. Take a picture of it fast. Oh, done. Sorry. No, I will be happy to go over it with you. I won't go over this particular one, but I can change things up pretty quick.
Yeah.
A source file and create another example and show you step by step based on the YouTube video and what to do. It is an important extension of our 50 class that we needed to continue with, because these topics, you're going to encounter similar kinds of analytical topics in the semesters to come. And what it is that I found is that we have an opportunity in 51 to kind of extend our learning of 50 concepts, which is what I'm doing in my daytime 50 class. My daytime 50 class is a full 17 weeks. So basically, I have the time to go over these topics over 17 weeks, the same way I'm going over these topics with my 50 and 51 class, because you're getting the same stuff. Okay. Yeah. So don't feel that just because, oh man, I should have enrolled in the full semester version as opposed to the half semester, I'm getting shortchanged here. No, you're not, because you're going to get it. You're getting it in 51.
Okay.
So, no, very good question. I'm glad you brought that up. And Ivan, I sent out those parts yesterday.
Yeah,
so
I got them. I can grab the board.
Since he gone, I have a question too.
Please, yes, go ahead, Victor.
Okay. What's the pros and the cons of using the equipment available that we have to resolve the issues instead of doing manually?
What are the pros and cons of using the equipment that we have to solve the problems or issues as opposed to doing things manually?
Yes.
So let's be more specific. Which issues or challenges or problems are you referring to?
Calculation, resistor calculation.
Yes.
If I use the calculator, for me it's faster than actually doing by paper or by hand. I just input the values on it and
yes,
get the final value at the end.
Yes.
Without actually do it every calculation by hand. Is that okay, or should
it's perfectly okay, because the bottom line is
the same.
If it works,
yes,
if you check it using Kirchhoff's voltage law, using Kirchhoff's current law, the bottom line is if everything balances, that's the bottom line. Some of us will be able to do it this way, just work it out on the calculator, pop some numbers down without having to do the redraws. But it's my responsibility to take everybody from 0 to where we need to be. So that's why my explanation is extended. That's why I think that particular YouTube video was, I guess, almost an hour, just for that one topic. And then the one topic really works best if you have reviewed series voltage sources, series opposing, series aiding, and then also, in addition to that, if you had also reviewed Kirchhoff's voltage laws, Kirchhoff's voltage law, Kirchhoff's current law, then and only then are you able to truly understand superposition, and you could just do it with a calculator, because you already understand how Kirchhoff's voltage law works. You already understand how Kirchhoff's current law works, and that currents coming in have to equal currents coming out. So you can do that just with a calculator in your head without having to do all the redraws. But for us mortal men, us common folks, and I'm a very visual guy, I like to show it completely worked out on paper so people have what I call a roadmap. Some of us have the roadmap up here, some of us need to see the roadmap on paper, and that's why the lecture took as long as it did, that go around. Okay, okay. Yeah, you're very welcome. I appreciate that. So, the bottom line is, if you can get to, so here's the solution set. If you can get to these currents, now that's why I wrote down these voltages are not required. We're spinning our wheels. Well, not say spinning our wheels. It's an additional exercise to calculate these voltages in this area. And yes, we could calculate, and yes, we could do the algebraic sum, and yes, we would end up with exactly the same numbers here. But that's one more layer of work that we don't have to do. If we do everything just using current direction and using current values, boom, we got it. It'll work out just fine. So yeah, we will talk about that, and I'll probably give us a redrawn version of this for us to do. So let's see. Okay, we are presently 5 minutes past the hour. Everybody who was invited is invited, and if they're not here by now, bad on them. Welcome, Oscar. It's good to see you. Izar, Gerardo. So Gerardo, yeah, we missed you last week. Did you happen to have any questions following up from last week, my friend?
No, I think I should be good. Sorry about that. I was under the weather.
Oh, no, you don't have to apologize. I just want to make sure if because you were out, and I don't mean to point that out or diss you in front of your classmates. I just want to make sure that if we discuss something and there was some question in the YouTube that wasn't clear, I wanted to make sure I would answer that for you. So no, different ones of us are caught in that situation where sometimes we can't make it to the Zoom meeting, and we will catch it later because the co-guy records this and you'll have it in a YouTube recording. But nothing beats being here with here's Nabil. Nothing is better than actually being here in the midst of your classmates, and as you hear the questions, you might come up with a question, but if you're viewing this as a recording later on, you can't throw your question in there that your classmates can share and benefit from, right? Yeah,
right,
there's
right.
Nabil, he's joined us. Yeah, so that's the reason why I point that out.
Yeah.
And to that point, what the administration has asked us to do is we're teaching our courses in this part of our semester very much the same way that we will be during the summer and possibly part way into the fall. We'll see. And what that means is we will have a regular class time that we are going to meet. And for us, it's whatever's scheduled on the master schedule, which happens to be Tuesday nights. But, and then I've been taking pictures of, at the end of our session, who's been on and so on and so forth, so that I can do record keeping. But here's what the administration has shared with us. They say, in no way, shape, or form are we going to hold the student responsible for being at that Zoom meeting at that appointed time and hold that against the student, because there may be technological issues. There could be Wi-Fi issues. There could be hardware issues. So there's other issues that the student it could be illness, it could be any of a number of things. As long as the student catches up with the Zoom recordings that instructors make, and I found the easiest way to make the recordings is I use Zoom, and then I transfer it to a software called Camtasia, and then I edit it, and then I transfer it out of Camtasia into YouTube. So it's a lot of video editing that I do in order to get it onto YouTube. But what I like about YouTube is on my channel, you can pick it up on your phone anywhere. You don't have to go to Canvas to look it up. And so that works really, I think, the portability of that information to get immediately in your hands. If you're at work and you have a 20-minute lunch break or something, you get the sandwich in one hand, boom, you've got your phone, you could be looking at YouTube and looking at the lesson and without having to open up Canvas and without having to go to a certain week, having to go to a certain module. Anyway, welcome, Nabil. Everybody say hi to Nabil. So Nabil, I've asked Nabil to join us so that he can bring us up to date on several things, and we can bring him up to date on some of our needs. And so the topic of the week for soldering is the very first time that you all will be working with surface mount technology. And surface mount technology is, there happens to be 4 tiny surface mount technology LEDs. They are so tiny, if you lose it, Don't lose it. Okay, if you drop this in your carpet somewhere, you will not find it. It is that tiny. But there's a certain way that we will be using these and a certain way of testing these, which I will talk about. But I wanted to take this opportunity, since you all have this, this particular board and project is a challenge if you do not draw things out first. So you will be asked to solder things directly to the board. And the one thing that is going to be soldered directly to the board is the chip. Okay, let me bring this up here. And speaker view. Okay, will be this particular chip. This particular chip is not included with a socket. So yes, you will be soldering directly onto the pins. You're going to have to use a light touch when you solder on here because there is no socket. So that serves as a reminder to me in your next week's project, actually this one's pretty straightforward. This one's all mapped out with traces and such. But your next week's project is what we call I've nicknamed it the squealer. And since Nabil is on the phone right now, is on the call with us, I would ask him when he packages these guys, is to package this with a socket. We included sockets in the kits for last semester, but the kits that I have, one sample kit that I happen to grab for the squealer circuit for next week is all of these parts, and there is a circuit board. Let me get it out of the bag. There's a circuit board, and this circuit board only has traces, but there's no trace pattern. There's no traces on this side, so it's not plated through. So your components go on this side, and the wires are soldered on this side. Well, if you compare these two boards, you say, well, wait a minute, Co. On this board that we have this week, there happens to be a trace pattern, which is nice. That means all of the wires for the components are interconnected with each other, and all we have to do is pop in the component, solder the ends like we have been, and everything is hunky-dory. The thing that we do have to remember, since we are directly soldering a chip onto that board, since we're soldering this chip directly onto the board, is be sure not to heat the pins too much such that they burn out the chip. But as we move on to next week, so next week, Nabil, if you could remember, on this particular kit, this is 1, 2, 3, 4, 5. So it's a 14-pin chip. I would strongly encourage us to provide the students with a 14-pin socket. This way, they're not soldering directly onto the pins of these 14 pins of the chip itself. Okay. So if you could remember to include that, Nabil, I would appreciate that very much. So on a side note, let's talk about what's happening after this week. So this week, it will be the 555 timer board. It will be with the 555 timer chip and the surface mount technology. After you finish soldering this project, you have nothing else in your hands, right? We have more things for you. So coming up for you will be this project. And this project, I encourage you all to read ahead of time the lab procedure, because you need to draw. Oops, this goes this way. Yeah, you need to draw the wires as they go from point A to point B, and you're going to put in hard wire. You're going to put in wiring that has to go from point A to point B, and you have to make sure that the wire follows the schematic. So this is the first time that you're going to be challenged in interpreting a schematic and then changing that interpretation up here and how you read it to the wires that have to crisscross as they go across this particular board, okay? So for next week, okay, I have someone else coming on in the waiting room, 2 more people in the waiting room. Let's get them on. Admit all, Brandon and Edwin. Okay, all right, so now we also have Brandon and we also have Edwin on the call. So let me move this over here. Hello, welcome. And here we go, over here, and all right. So let's see, we are presently 14 minutes into our discussion. So are there any questions so far? For the two guys who just joined, you're saying, what did I miss? 14 minutes. He must have said something in the past. It's okay. I'm not slapping your hands. So what I've asked Nabil to do is we have three more projects after this week. This week we're working on the 555 timer on this particular board, and we're with the surface mount LEDs. After you're done, there's three more projects, which means you're gonna have to work out sometime according to Nabil's window of opportunity, starting next Tuesday, to go pick up your three remaining projects, okay? And the three remaining projects, one goes back to week 1 of our canvas, and that is a DB9 cable. And the DB9 cable is one of the projects. Another one of the projects will be this APC squealer project. And this particular guy will make all kinds of wonderful sound depending upon how much light hits these photoresistors. So that's the second project. And then the third and final project will be your LED dice project. And the LED dice project, you think this week you have 4 surface mount components. For the LED dice project, you will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 16, 9, 18, something like about 18. And no, dice. 1, 2, 3, 4, 5, 6, 7. So 14. So yeah, you have 14 surface mount LEDs that you're going to be mounting on that guy, and that's going to be really intense. So this week's exercise is a preview for the final project of the semester, which is our LED dice. So after this week, how many projects do we have ahead of us? 3, okay? So Nabil, if you can address, have you thought about yet what window of opportunities might exist on Tuesday for our group to be able to come by and pick up the 3 remaining kits? Your mic, sir. Thank you.
Okay, looks like Tuesday between 1 and 2. That's probably the best time we can do this.
Tuesday, 1 to 2 p.m. Okay. All right.
And I'll send out an email giving a protocol of how you have to show up. Essentially, we have to get an arrangement ahead of time of what time each student is going to get there. And that day before you come to your scheduled appointment, you have to call in, and the school has this protocol now that we have to ask you 3 questions, and it pertains to the symptoms. Do you have a fever? Are you coughing today? And what was the last one? Coughing, fever, and are you having difficulty breathing? So if you answer clear for all those questions, then we can have you come by to pick up your item. Of course, with the county ordinance that was just, or the county directive that was just passed, you have to come in with some kind of a face covering, whether it's a mask or a scarf, or you know what I mean. You all have seen these things already. So if you have gloves, that would be better for yourselves as well. But essentially, come into building 1600, room 1602. I'll have the door propped open, and we'll go only 1 student at a time. So that's the point of having the appointments, is so that you get there at this certain time. By the time you leave, the next person gets there, there's a gap in between. Okay, I think that's really all that needs to be done.
Cool. Okay. Does everybody understand the procedure of what has to happen in order for you to go on campus? You have to let Nabil know that So Nabil, they will have your cell phone in order to contact, the school issued you a cell phone?
Yes, they'll have that.
Okay, what is that number so I can jot it down?
Give me 1 second.
I can look it up from your call earlier too, so let me do that.
Better email us, right? Or
No, the cell phone works most directly. 510-427-1119, is that correct? He's checking to confirm. That's a number that I believe we had communicated with each other on earlier today and yesterday. So yeah, I believe that's correct. 510-427-1119.
Yeah, that's correct.
Okay, we're good with that? Okay. All right. And
Can you repeat the number, please?
510-427-1119. Very welcome. Very, very welcome. Okay, cool. Now, the date was which day next week, my students? It's Tuesday, and the time is between 1 and 2. So between 1 and 2. And so based on next Tuesday between 1 and 2, who can commit to being there next week between 1 and 2? And I'll start marking names on the paper now. Izar, can you be there between 1 and 2 next Tuesday?
Yes, I can.
Okay, 1 to 2 p.m. All right. Oscar, can you be there between 1 and 2?
Yes, I can.
I can't hear you, sir.
Yes, I can.
Okay, Oscar, 1 to 2 p.m. Victor Montano, 1 to 2 p.m.
Yes, sir.
Okay, 1 to 2 p.m. Brandon Nguyen, 1 to 2 p.m.
Yes, sir.
1 to 2 p.m. Gerardo Sanchez.
Yes.
Okay, 1 to 2 p.m. Ivan Suarez.
Yep.
1 to 2 p.m. is yes. That was a yes.
Yeah. Yes.
Yes. Okay, and is Edwin Sanchez with us?
Yes, I'm here.
Hey, there you are. Hi, Edwin. I didn't mean to skip you.
I'll be available.
Okay, 1 to 2 p.m. Okay, great. So everybody who's present on the call right now, 1, 2, 3, 4, 5, 6, 7. 7 people will have committed to come by next Tuesday between 1 to 2 p.m. to pick up parts. And the process is when you get to campus, before you exit your car, you call Nabil at this number, 510-427-1119, 1119, and you have to answer those 3 questions. And the 3 questions are,
Do you have fever?
do you have a fever? Do you have a cough?
Shortness of breath.
And shortness of breath. Okay, and shortness of breath. And if you're yes to any of those, then it's not going to work. Okay? Okay.
So Frank, I think we should assign, I think we should assign them a time now, like a time slot of someone comes in at 1 o'clock, someone comes in at 1:07, someone comes in at 1:14, etc.
Okay, yeah, that way you won't have everybody waiting outside at the same time. Okay, we'll just do this from top to bottom. So since you have a time frame of 1 to 2 p.m., I'll just start from the top. Izar, can we commit, let's see, 1, 2, 3, 4, 5, 6, 7. So roughly 8 minutes apart. So let's go do this. Izar, can we commit for you to be there at 1 p.m.?
Yes.
Okay. Oscar, can we commit for you to be there at 1:08 p.m.? Oscar? We can't hear you, Oscar. Your mic's not.
Oh, okay. Sorry. Yes.
1:08 for you. Okay, Oscar? Okay. And then Victor Montano, can we have you commit to 1:16 p.m.?
Yes, sir.
Okay. And then Brandon, can we have you commit to 1:24 p.m.?
Yes, sir.
Thank you. Edwin Sanchez, can we have you commit to 1:32 p.m.?
Yes, sir.
Gerardo Sanchez, can we have you commit to 1:40 p.m.?
Can I request the last time slot?
Okay, then Ivan, can we ask you to commit to 1:40 p.m.? 1:40.
Yeah, 140.
Very good. Okay, 1:40. And then the last time slot, Gerardo, that would be 1:50 for you. Is that all right?
That's fine.
Okay, so 1:50 p.m. So I will read this. I'll share this information I've written for Nabil, so he will get a copy of this. So to confirm, Izar's at 1 p.m., Oscar's at 1:08, Victor Montano's at 1:16, Brandon Nguyen's at 1:24, Edwin Sanchez is at 1:32, Ivan Suarez is 1:40, and Gerardo Sanchez is at 1:50. Okay? Okay. All right.
And so one more piece to this.
Yes.
When the call is being made, try to make the call before 1 p.m. That way, while I'm issuing out these items, I'm not trying to call or deal with the phone. So call me somewhere between 12:30 and 1 p.m. is probably going to be best.
Would it be possible to text you the answer to the 3 questions?
Oh, no. The reason is because they want us to hear your voice. So if you're coughing and you're feeling sick, it might be relatively easier to hear it versus a voice message or a text message.
Did everybody copy that?
Yes.
Okay, so you are to call Nabil between 12:30 and 1 to get the clearance. So do not call him after 1, because if you call him after 1, he's engaged with students, and it's going to be awkward for him to deal with trying to answer the phone and engaging with the student who's there after 1 o'clock. So please call him between 12:30 and 1 p.m. Cool. Anything else for Nabil before we let him go? So I do have one more. Yes. Yes, please.
Victor, I don't know if it's pertinent to Nabil or not, but the project that we have for the case maker. So
Yes.
I hear at least one more student having issues with, I got all the way to step number 3. I cannot add the graphics onto the board.
Okay, I have a solution for you. I have a solution which I will show you. So that does not pertain to Nabil. Okay, okay. Does anybody else have anything else for Nabil?
I might
yes.
request, see if he has time later tonight regarding the other class. Nabil, maybe you could tell me now if you have some time later after the class for some software update or upload for another class.
Okay, I might have about 30 minutes, so let's see what we can do with that time after the class.
Right. Your help, by the way, was great. Everything's good except for I got one little problem. And 30 minutes should be plenty of time, I think. Thanks. I'll leave you. Thank you.
Okay, and I'll leave it for you two to communicate with each other. Our time frame together is between 6 and almost 7:30. And then Nabil is going to be with me on another call starting at 7:30 for at least 10-15 minutes. So anything after, say, 7:45 that could fit Nabil's schedule may be possible. Because Edwin, you're with us until we're done with this session here, which will bring us very close to 7:30. Okay? Any other questions for Nabil?
Mr. Go, I have one question for you.
Yes, sir.
So for the Squealer lab or that project,
yes,
do they need wire or can they just use the leads that are in there with, you know, bending the leads from the components themselves?
They can bend the leads up to a point. I think that they should have some extra wire so that they can make the necessary bridges that have to go from point A to point B. So if we cut them a length of a very small gauge solid core wire as opposed to the stranded. The solid core will be easier to heat and easier to attach the solder rather than the braided. The braided tends to fray and it tends to not take the heat evenly, and then we end up with a bigger mess. So if we could, I would encourage the students just use whatever cut leads that are cut to use those, but they have to be extra careful. And I'll talk about this next week more, but I say to answer your question now, probably an additional length of maybe a foot of insulated wire or solid core, maybe one of each. 12 inches of solid core, 12 inches and they're both solid core, but 12 inches of insulated or maybe 12 inches of bare wire, and then let the students decide how they best want to route their wires from point A to point B for the squealer project. Is that something that we can include with the sockets for this guy?
Yeah, 12 inches seems like a lot, but yeah, it can be done.
Okay, all right, I appreciate that. Yeah, since we have just 7 candidates to be concerned about. Okay, okay, all right. Thank you very much. Now, does anybody else have anything else for Nabil? Okay, I do. I want everybody to turn off their microphones right now and thank Nabil profusely for everything that he does on that end to help support us. Yay! Yay, Nabil!
Thank you.
Go guy.
All right.
All right. So thank you, Nabil. I will we'll chat again for the 7:30 class. Okay. Thank you. Adios. All right. Now for our class, a couple of very, very important things, and that is testing your surface mount LEDs. The kit. Let me go ahead and change. Get my camera in view here, and let's go ahead and do this. Switch. Come on, mouse. Come on, mouse. Be nice to me. Running out of mouse space. There's the mouse. Okay. Go to the camera. Okay, so now we're on camera view. Ooh, and this is also going to be challenging. I'm going to turn off this light because it's a little bright, and then let's see, here is correct. And let me put this guy on here so we can have something to focus on. Press the focus button. Okay. All right, so now it's focused. Here is a regular LED. Here is your surface mount LED. A regular LED is simple enough to work with and deal with because you've done this many times over. A regular LED, you can identify positive from negative based on the length of the lead. It's positive to be long, it's negative to be short. And this is easy enough to tell, so you can set this up with proper polarity. Now, how can you tell if an LED is burnt out or not? Well, you can use your battery pack. So here's your battery pack. And here's the 2 leads of the battery pack. And the 2 leads of the battery pack are packing 4.5 volts. And we are very concerned about using too much voltage on this. So this will work just fine. I have to use a resistor. And one of the resistors in your kit is a, what is this? Looks like a red, yellow, brown. Anyway, it's a red something. It looks like a red, yellow, brown. So this is in the hundreds. So 240 ohms. So 240 ohms is great. What I'm going to do with this is I'm going to attach one end of the resistor and hold it to the positive lead. I'm going to bring my negative lead up here, hold it between these 2 fingers, move this out of the way, use this for contrast, or maybe not, better use it for contrast, and bring in my LED and see if I can get my LED to light up based on the polarity of how I'm going to do this. So let's see. Yes, the LED is lighting up. Does anybody see the LED lighting up? Not lit, lit,
Yes.
not lit, lit, not lit,
Yep.
lit. So this is how you can test the LED and confirm the polarity, yes? Now, you have to do the same thing with your surface mount LED, my friends. Your surface mount LED, and I'll put this guy back in the picture so that you can get a sense of scale. This little tiny thing, if you look at the back side has 2 soldering pads. Let's see if I can catch it on the light here. It's kind of tricky. It's very tiny, but there are 2 gold-plated pads where the soldering can take place. This has to be flipped this way. It sits on the board, and the LED is that little dot in that little white space. Now, to test the LED, I'm going to take my resistor, and I'm going to connect it to the positive lead right there. So this is the positive end. I have to have a current limiting resistor to do this test. If I don't use the current limiting resistor, if I take my leads and connect directly to the LED, you will have burnt it out. So watch carefully. What needs to be done here is we're going to check the polarity. I have the negative lead in this hand. I have the positive lead in the other hand with the resistor. And if I touch it a certain way, you see it light up? And again, oops, don't flip over on me. No voltage. And now, does it light up for you? Oh, my hands are in the way.
Your finger's in the way.
My finger's in the way. I just noticed that.
Yeah,
Sorry.
but it turned on the previous time. It works.
So here it lights, no lights. Here it lights, no light. Light, like that, and no light. Right there. Is it clear how you test for the polarity of the LED? The one side of this is negative, one side of this is positive. And if you get the LED backwards on your board, there's very little chance that you can save it. Very little chance that you can save it. Yes, my friends.
Yeah, your positive on the LED, there's SMT.
Yes.
It is the top side right now, right?
Well, no, here, let's say this. There happens to be on the LED a very, very small stripe on one side, and that stripe on one side should indicate cathode, should indicate the negative side of the LED. So that stripe on this LED presently, and I'll try to have this focus again onto the okay, it's focused on the board. It's as close as I can make this. So there's the stripe is on my right is on this side, and if I bring my negative lead here to confirm, and I go to touch, and it lights up. Yes. So whatever when the LED lights and the black lead touches that side of the LED, that is the negative side of the LED, right there. And the positive side is where I'm holding the resistor. So I'm holding the resistor on the positive side there, and I'm using the resistor wire to go to the positive side of the LED, and it lights up. So when this goes on the board, my friends, when this goes on the board, it goes on the board between these pads right here. And it's marked LED 4, LED 3, and you have some surface mount other components, your surface mount LEDs. And so this has to sit right there on that pad in order for you to do the soldering. So my recommendation for you all when you go to do this is to put a spot of solder on that pad first. So there's 2 pads. There's a positive pad and a negative pad. Put a spot of solder on the pad first. And then the orientation, follow the directions that are specified for this. I'll open up Canvas in a moment so we can look at this. And then you place your LED very carefully in the appropriate orientation over the pads. And my recommendation is probably have something weighted to hold it down. You might use an eraser or something just to hold it down, because what you're going to do is you're going to heat up gently with your iron over this side, and whatever solder you've already put on the pad will just melt to make connections, and then you will put your iron gently on this side without moving the LED, and then melt the solder that's already on the pad. So the procedure is that method. Now, there happens to be associated with this, and in this week's Canvas, several videos on surface mount soldering that you need to watch before you begin to attempt this, okay? Don't attempt to do any surface mount soldering until you have reviewed the videos on surface mount soldering first. That will give you a clue, some helpful hints and suggestions on what to do. Otherwise, the rest of it is pretty much as it was before with the other components. And these things are so small. If you lose this, if you burn this out, is no bueno, okay? I will put this back in the little holder later. I won't want to attempt it now because it'll take me a good 10 minutes or so, 5-10 minutes to get it back in there for safekeeping. And then I'll put tape over this so it won't fall out. Are there any questions on this week's kit? There ain't a whole lot of parts on this, my friends. I'm going to take the battery out of my battery holder. Okay, so the parts are a 555 timer chip. You have a green LED, a red LED, and then you will have 2 surface mount resistors, and you will have 2 surface mount LEDs. And we already determined this particular one, not only the polarity, but also, let me get the right resistor. And don't use just any resistor. Use the 240 ohm resistor. And we've also determined the color of this LED. So this particular color, in my eyes, oh, come on, quit dancing around, honey. Backwards. Turn that around. Backwards. Turn that around. Oh, put the battery back in, Co. Funny guy. There. This one's a green one. And then the red one, when you light it up, will appear red. So you want to make sure the green LED, the surface mount LED, goes with the large green LED. And you want to make sure that the little red surface mount LED goes with the red LED. So do not mix them up on the boards. I've had students do the soldering and they're so in tune with getting the surface mount process done correctly, they totally forgot, oh, gee, I've got the red surface mount LED with the big green LED, and I've got the surface mount red LED with the wrong color big LED. So red's on one side, green's on the other side per the instructions that came with the lab exercise. So in all, there happens to be 1, 2, 3, 4 resistors. There's only 4 resistors here. And there happens to be a capacitor. There happens to be another capacitor. So you have an electrolytic capacitor, a ceramic capacitor. You have the 555 timer chip. You have the board. And there also happens to be these guys. These happen to be point contacts for voltage source. And so they are soldered onto here. This is your jumper 1 and jumper 2. Somebody was asking on the schematic in the multisim, what was JS1, what was J2? Jumper wire 1 is going to be one of these guys, jumper 2 is going to be the other one of these guys. And the recommendation here is, although they're connected together in tandem, you use a wire cutter, and the wire cutter will cut this particular guy in 2. Okay, so then you'll have 2 of these pieces, and then you will have one end go here, put the short end in with the long end up, so that the long end will be sticking up off the board, and so you'll be making your connections with voltage using your leads onto, using your battery leads onto the jump J1 and J2, okay? So that is really all there is, and it may seem like, oh, it's brainlessly simple, there's only a few parts, but this is your first foray into surface mount technology. Do not apply too much heat on these guys. You'll burn them out. Do not lose these guys. If you lose these guys, I don't have these for ready replacement. Do not even attempt any part of this until you've looked at the surface mount technology videos. And when you're soldering the chip in place, very important, make sure the orientation of the chip is correct. The orientation of the chip is set up such that it goes on the board right here, and there's one square pad. That one square pad on the board is where the notch side of the chip goes. Notice that the chip happens to have a notch on one side, so the notch is pin 1 and identifies pin 1, and it goes in that way. So that notch faces your LEDs. If you put this guy in backwards and you solder this guy in backwards, you're toast, because it's going to be incredibly difficult to unsolder 8 pins on the backside to remove this in case if you happen to make a mistake and wire that chip in backwards. Okay, so the chip has to go in with the correct orientation. The notch is facing your LEDs. How do we know that? Because the pin that is right next to the notch is pin 1. And how is pin 1 identified on the board? Pin 1 is identified on the board by virtue of a square trace of these 8 that are set up for the chip. Okay, when you do have the chip in place and the proper orientation and you're ready to solder the pins, remember, because you're soldering the chip directly, you don't have the benefit of a socket in this particular case. You're going to use just enough heat on the pin and the trace to heat it and take the solder and immediately go to the next, go to the next, go to the next. Don't leave too much heat on the pin, otherwise you'll burn out parts of the chip. Any questions about the chip, its orientation, and what concerns we have about soldering it onto the board? Okay, another question that came up, which was really, really good last week, and I addressed it in my several emails that I sent out over the past several days, and that is, wow, I happen to have put so much heat on one of these traces that it burnt off the board. So am I going to get a whole new board? Well, no, we don't have boards readily available for students to make a mistake on and just give them a brand new board, but there's a learning exercise. And the learning exercise is, if this trace over here for this particular component is burnt, and you don't have anything for that wire to solder to, well, you still have a little wire over here. And so where does this trace connect to? This particular trace connects to this point over here. So you follow the trace from where you've lost it, it's burnt off the board. You follow the trace that's on the board to the next connection point. Ah, it goes over here. So whatever device was here, you simply use the leftover wire, and you have leftover wire for each one of these, a lot of leftover wire. After you solder the LED on the board and after you solder resistors on the board, you have a lot of leftover wire. You just simply use one of those leftover wires and you solder one end of the wire to this component at this point, and then the other end of the wire to the wire that's sticking up out of this hole that has nothing to solder to. You are going to make a repair, and that's a very important skill for technicians to learn in case something goes wrong on the board, like a burnt trace. So it's a great learning experience for you to learn in this particular case. So, don't let burnt traces ever upset you, because burnt traces are repairable by bridging. So the technique is called bridging. And in a more recent, so the technique is called bridging. Any other questions regarding this week's kit that I can answer for you?
Yes. In proper technique, you're not supposed to use the tip of the soldering iron, but in this case, would you, or would you still do the same technique and try to? So
answer the first part of your question. To answer the first part of your question, yes, we usually, so pretend that this pair of tweezers is the point of an iron. Mm-hmm. We usually use the shaft, the shank part of the iron right here to heat up a wire while it's sitting on the board through a trace. In this particular case, because we're soldering the pins of a socket, and let's go ahead and put the socket back on here for a moment. socket back on here. Flip it over and let it sit down here. So in this particular case, for these socket pins, I'll hold this at an angle. If I'm going to come here and solder, I'm going to use not the point of it, but very near the point, because I have to heat both the trace and that chip pin both simultaneously. And I count my 1001, 1002, 1003, 1004. Then I bring in my piece of solder and let that melt, and then I bring both away. So in this particular case, very near the tip, but not the tip. In the instance of the surface mount, you will be using the tip. So if I come over here and I grab my surface mount component and I put it on the pads, now, as I've said before, you will already have put a little tiny bit of solder on the pad here and here. Then after that's cooled off, you will then make sure that the LED is in the proper orientation, negative to negative, positive to positive. Then what you're going to do is you're going to come up to the edge of this surface mount component. You're going to heat the pad, and whatever solder was there will melt. And whatever solder that was there will melt and attach to the underside of the LED on this side. Then you flip the guy around. When you flip the guy around, then you bring the soldering iron over this side and you just heat the pad. And as close to the chip, as close to the LED as possible. It might help, it wouldn't hurt if you had something for your first soldering attempt, have something to help hold this down. Whatever that something is, a pencil or something that will help hold it while you attach your iron to the edge right here. It will go very quickly. And then the videos again are very good, and they will go over these details again. So definitely do not attempt to do any of this until you've watched all of the videos that are on Canvas for surface mount soldering. Okay, good questions. I appreciate that, Brandon. So normally we use the shank. In this particular case, we will continue to use the shank of the soldering iron, but very close to the tip for most components. And then for the LED, for the surface mount devices themselves, we will use the very tip itself because the point of connection is so small. Any other questions regarding the kit? Okay, all right. Let me set that guy aside.
I have one.
Yes.
Schematics.
And what about the schematic, my friend?
They don't come with my kit.
Let me switch this back. Wrong mouse. Wrong computer, wrong mouse. Sorry. Let's go back here. Okay, so let's take a look at this here. And let's go to our class 51. And it's no longer here. Week 5 assignments, 555 flasher assembly. Here's the document for it. Let's go ahead and open this guy up. Let's do this. Okay, so let me go ahead and share this screen with you. Share, and here. Okay, so from Canvas, I went to our week 4 project number 7555 LED timer flasher. Oh, clicked on the Word document. It downloaded and opened up the Word document, and here it is. So this is our 555 timer. It's week 5, 555 flasher assembly, and it goes to show the necessary parts and more details around the parts, a good description of what's happening. Let me go ahead and see if I can magnify this a little bit. Yay. Okay, is this a little easier for you all to see? So here's the capacitor, here's the 555 timer chip. There's a notch right there. Sometimes in place of the notch, there may be a white strip. So that means this particular pin is pin number 1. This pin that's closest to the notch on this side, as you're looking at the top of this device, is the pin that goes into the square-shaped soldering pad. Your resistors are given here, and it is the 240 ohm resistor here that you will be using to test your LEDs. Okay, now you also have surface mount resistor, so that's a little guy like that as well. All right, then capacitor, these LEDs, then finally these guys. So the green LED is shown with having a magnifying glass is a good thing. So the green LED is shown with a black stripe, and the red LED is shown with the green stripe, and the stripes indicate what they call cathode, and cathode is your negative side of the LED. And then your components go on the board this way. So it says you happen to have your resistor here, LED here. And if you look at the LED very carefully, does it show I'll make this bigger. Okay, make it bigger. All right. It shows very clearly that the cathode has to be on the top. Okay, the cathode has to be on the upper pad, the anode has to be on the lower pad. So the cathode is the negative side of the LED, it has to face the top, and the anode is the positive side of the LED, and it has to face the bottom. You got to make sure that you put red with red and green with green, okay? Other than that, the rest of the components are pretty basic. You got 4 different resistors, and they're labeled R1, R2, R3, and R4. And the values for the resistors are specified. R1 is a 10K ohm resistor, R2 is a 100K ohm resistor, 3 and 4 both happen to be 240 ohm resistors. So make sure you follow the labeling, follow the capacitor labeling, C1, C2. C1 is 10 microfarads, C2 is 0.1 microfarads. And so as long as you follow the labeling carefully, then your components will go on the board correctly. So LED, capacitor number 1, capacitor number 3, and capacitor, your jumpers go here for J1 and J2. So any questions regarding what goes on the board and what H stands for hole. So there happens to be hole number 1, 2, 3, and 4. So they don't matter to us. We have no components going in there, but your devices go on the board in this fashion. So Victor, even though, or was it Victor, you didn't have documentation? This serves as your documentation as to what needs to go where, okay? And LED number 1 goes with number 3. So LED number 1, red, and LED number 2 is green. So LED number 1 is red. That means it has to hook up with the appropriate LED number 3. That is also red. So 1 and 3 go together. So red is on this side of the board and green is on this side of the board. So this is 2 and 4. Okay, any questions about the orientation there? Red on this side and green on this side. Okay, so you solder the parts on the board, follow these directions, and yeah, it's going to be a fun project. And so based on you being able to hook power up to this, these LEDs should flash back and forth the same way that you were able to get your multi-sims to flash back and forth in your multi-sim exercise. Okay, any questions about that? Any questions, any more questions regarding this project?
No.
Okay, all right, so we will put this project behind us and move on to bigger fish to fry. Okay, let me come back to unshare. So let's go to, oh no, sharing is fine. Yeah, maker case. So maker case, makercase.com, boom. And in my rewrite of the directions and most recent I sent out, everybody can see the maker case site on my screen right now. All right, so in my most recent stuff that I sent to you, some people were stuck on step 2 or step 3. So we go to basic box like this, click this guy, And before we go any further, don't start loading up dimensions here because it won't work. You have to go all the way to the right-hand side. On the right-hand side, it says, looking for old version of maker case. Does everybody see this on the right side of the screen? This is what you have to select. If you don't select this and you start popping in numbers in here without reading my revised information, you'll never be able to finish this project. So you click on the old version. Now watch what happens to the box. The box decidedly changes its view when I go to the old version. So click. Boom. It's a totally different box. It works the same way. Okay, I can spin it around, rotate it left, or do all kinds of things. But now I can enter the information. So I want to make sure this is in inches, make sure that this is, I believe it was 3.5, 3.5. Where's my decimal point? Point, period, 0.5. Where's my num block? Here's my num block. And then this guy is a 1, and this guy is a 2.5. And these are outside dimensions, 1/8 of an inch. We're going to have finger joints. And on the finger joints, you need to make sure that this was set to 0.2. So you adjust the finger joints tab width down to 0.2, and so it's set to 0.2. Once that's set, and then you click on the top. And when you click on the top, another set of dialog boxes come up, and in the top, what you're going to do is fill in the rest of this according to the instructions. So if you were using if you didn't go to the old version, you would not ever be able to get to this other menu. And so all you have to do is finish this up. And when you finish this up, then you will generate laser cutter case plans. And then you'll save this. You should always save the file. But you generate laser cutter case plans. That generates what we call an SVG file. And that SVG file is what you need to port over to a drawing program like Visio or something else like I'm going to show you. So if you have Visio, great. If you don't have Visio, there's something else that we can use. I use the Visio, and in my let me get to here. In my notes, I gave you all a preview of what you can do with your box. And so co-maker case in Visio output example. So I did this as a drawing. So here, check this out. Hey, you get to do all kinds of fun things like this. This is what I was talking about, where you could enhance. And what's really nice about this is you can customize it any way you want. This particular part is your top, and it will be cut out for your circuit board to fit in. So there's no drawings or any lettering you can put on the top. This is one side. This is another side. This is another side with the logo with our class. And then you still have one more side, and you also have the bottom side. And so what I've done is I put in tattoos of a whale and tattoos of my favorite other animal, sea turtles. And when this goes on the laser cut in tattoo form, it'll give you a really, really nice image laser cut into your wood boxes for your design. Now, you don't do this in Maker Case. You have to make the Maker Case first, save the SVG file. Then you have to go to a drawing program like Visio or like Inkscape, which is what I'm going to show you. We're going to do this in Inkscape, and then put this information in Inkscape. So what I've got going is, if I go to inkscape.com, just go here. Let me stop this. Actually, I can do it up here as well, I think. Yes. So here we go. Let's go here, and I'm going to type INKSCAPE, inkscape.com. Hit enter. And can everybody see Inkscape?
Yes.
Okay,
Yes.
cool. And then for Inkscape, oh, it failed to load. Okay, so let's try this again. Inkscape.com, and let's do it. Load again. Website name. Oh, let's see, what did they do? INC, hold on one sec. INC, did I spell that wrong? Inkscape, Inkscape. Okay, INT, Pearson. Let's go back. And let's go back. And let's go back, and get Inkscape. So I'm going to go back here. Inkscape, draw freely. Okay, so instead of .com, let me do this. Go here and go to Google. And then search here. K-S-C-A-P-E, Inkscape, and hit enter. And then I want this, get Inkscape. Well, that's why it didn't work. It was in inkscape.org. Okay, so draw freely. Inkscape. Now, which one did I get? I went to the Microsoft Store. Oh, okay. Is that the same? No. Let's come back here. Inkscape. Twitter. Microsoft. So get Inkscape from Microsoft Store. That's the one that I got. Inkscape, Microsoft Store. Free. Hit get. Open up Microsoft Store. And as we open up Microsoft Store, it'll allow you to download, it'll allow you to launch, and it tells you the product after it's installed, it's installed. It's very fast, it's free, takes very little time. So again, what it is that you want is not inkscape.com, but what it is that you want is Inkscape from the Microsoft Store, okay? So when you do get it up and running, this is what the guy looks like. So you open it up, and if I go to new, it'll look like this.
Yeah, we can't see your.
Yeah, I know, I'm
screen
sorry.
now.
Let me port this over here. Here we go. All right, so this is Inkscape, and it comes with this. So you will go to File, and then you will open. And then on the open, you will go to wherever you have your case plan. So my case plan is here. This was my SVG file, case plans co. Select it and then hit open. And when I hit open, what I get, very nicely, not this particular one. Come on, let's close this particular guy up. Come on. Here. This one. Okay, when I open it up, guess what? I have, and it's very faint on here, I have all my laser cut edges on here, okay? I don't know if you can see it on your screen, but you can just make out the laser cut edges. And then so what we're going to do is we're going to bring in different objects. And so we will go ahead and let's take a look. We will go ahead and bring in, and you'll play around with this because I haven't played around with this particular guy. I did everything in Visio and ended up with my own creation, which I showed you a little while earlier. But you do your drawing in here, and when you finish your drawing, hopefully you'll end up with something like this. You'll be able to do different size fonts. You'll be able to select different fonts. You'll be able to go onto the net and import images. Do not import color images. Color images do not laser cut well at all. You need something that is black and white. That's why I chose tattoos. So these are tattoo images. They will laser cut beautifully because the contrast is very strong. And so once you have the bottom, the left, the right, the front, the back, all done, you save this file, and this is what you send to Nabil. Okay, this is what you have to upload and also send. So you upload for the grade for me, and you also send to Nabil. Okay. And then from here, what he'll do is he will convert this back to an SVG, shoot it into the laser cutter, and these will be cut. So at the end of our time together, when we arrange for a time for us to go back to campus, you will be able to then get your case that you've designed with your emblems, whatever you choose to put on here. And the more creative, the better. I really like some creative designs. You will use wood glue. You will glue the bottom and the sides together. The top is not glued in place because you have to mount your electronic dice board on here and assemble it. And then you have the box to containerize your electronic dice kit. All right. So it is, you find this under Inkscape, under Microsoft Store. Yes. And then download it. It costs you nothing. And then when you have it, you can open up your SVG file that looks very much like this, bring in your lettering, bring in your drawing, save it as an Inkscape file, send it, or Visio. Those of you who have Visio, this one is a Visio version. And Visio does many other things so well. I've used Visio professionally in my daytime business for almost 15 years, and I've used it in place of AutoCAD for doing all my computer-aided drafting. So Visio is remarkably powerful for many things. So if you've invested in Visio, it's a worthwhile investment that you've made, so you can use it for many things. So you can do this in Visio or you can do this in Inkscape. Any questions about this?
Nope.
Done. Okay, let's talk about superposition. Whew. All right, so for superposition, let's go to here. Let's go to YouTube. You spell it right, Co. YouTube. Okay, I won't be able to do a complete analysis with you for superposition, but let me walk you through the steps. So co-channel, go to co-channel videos, and on videos. So here are the associated videos that will help you with superposition. You have to understand series aiding. You have to understand series aiding and series opposing. So what do you do in a situation when you have batteries? What do you do when you have voltage sources that are aiding? What do you do to reconcile voltage sources when they're opposing? So you need to look through this video. And so if I have two, in this case, moving electrons to the left, because the electrons leave the negative side of the source, this one leaves the negative side of the source, but this one moves electrons to the right, where I happen to have two moving to the left and one moving to the right, I create a simple T-chart. I draw an arrow to the left, I draw an arrow to the right, and I write down the voltage values that are moving electrons to the left or the right. I happen to have two that are moving electrons to the left, 11 volts and 11 volts. I only have one that's moving voltage to the right. So this 11 volts cancels this 11 volts, leaving me what? A net of 11 volts. So that means these three will reconcile to a single equivalent voltage source that moves electrons to the left. That's my final direction, because whichever voltage adds up to be a bigger number, whichever column has a larger voltage, will be the dominant direction. And so the dominant direction of these three wired in series opposing is going to be to the left. So review this, listen to the dialogue, listen to the questions that were asked, and then you'll have a better understanding of series aiding, series opposing. Then we also had Kirchhoff's voltage laws and Kirchhoff's current laws. This was in your reading, but I wanted to make a separate YouTube discussion of what's happening with Kirchhoff's voltage and current laws. And let me find a nice spot where it's fairly clean. Okay, so Kirchhoff's laws, there's two of them, KCL and KVL. KCL is Kirchhoff's current law. There's the definition. Kirchhoff's voltage law, KVL, there's the definition. Fundamentally, it's this. The current law says The sum of currents entering any node must what? Equal the sum of currents exiting that node. Do I have a node in the middle of this drawing right here? Yeah. Do I have wires attached to the node? Yeah. Do I have currents written with arrows showing that the currents are going in and out around that drawing? Yes. So this is 2 amps coming out. This is 6 amps going in, 12 amps coming out, 17 amps going in, 4 amps going in. What's happening on this remaining wire? Well, you reconcile this very easily with an in-out chart. You write in at the top of this column, out on the top of this column, and just fill in what you got. You have a 4 amp going in, 6 amp going in, 17 amp going in, totals 27. What do we have coming out? 2 amps coming out, 12 amps coming out. Add that up, 14. Kirchhoff says this side has to equal this side. No ifs, ands, or buts. It's a law, like Ohm's law. So 27, if 27 is a higher number, it has to be 27 on this side. So that tells you something is missing on this side. What is missing on this side is 27 minus 14 gives you what? 13. And 13 fits in which column? The out column. So does that help answer what is on this wire? The wire answer on this wire is we have a current coming out, and it's of 13 amps. Because by the time we total the 14 plus the 13, this 27 total on the out has to equal the 27 going in. I'll give you another example over here. One node, all these wires with ins and outs. What do? A simple in-out chart. Write down all the values going in on the inside, write down all the values going out on the outside, total them up. I got 39 here, I got 33 here. What is missing? 39 subtract 33 gives you what? 6 amps. That's the missing current. Which column is the 6 amps in? It's in the out column. So therefore, it tells me my mystery current over here is 6 amps, and I have a green arrow drawing out because my in and out has to be the same. Who says so? Kirchhoff. And I apologize, I was supposed to have 2 H's in here. I didn't spell that correctly, but it's correct in the title. Then there's also a voltage law, and this is really good because Kirchhoff's voltage law says in any closed loop, as long as you have any closed loop, the algebraic sum of all the voltages in any closed loop must add to what? 0 volts. So if I go and scroll this video along and then we pop in these numbers and we refer to a previous, let's see. Yeah, we refer to a previous circuit that I had worked on. It is my series parallel 5R video. And if I pop this down for a moment and go back to here, you will find series parallel 5R. That's over here, okay? And it's this particular series parallel that gave us a final circuit that we're going to use for a reference. This is the circuit as we start. How do we analyze it? This video walks you through step by step to get to a redraw, and it walks you all the way back. And then we fill in all of these voltages and calculations and such. How do we prove all of this? We can prove all of this using Kirchhoff's voltage law. So I took my schematic from this particular one, 28 volts, and then these 5 resistors, and I used it for my Kirchhoff's voltage law example. So if I go back to Kirchhoff's voltage law, and here's my Kirchhoff's voltage law, mute this and go to here, and I go right to the end, almost to the end. Let's see what we can see here. Yay, all right. This is good because we have these voltages and we have these polarities based on the previous YouTube, but how do we know any of these are right? How do we apply Kirchhoff's voltage law? So Kirchhoff's voltage law, loop 1, is this a loop right here? See this little square on the left? That is called a loop. That loop happens to have 3 components in it, 3 resistors. And so if I start at any point and I go around that loop and I count the voltages up, they algebraically add up to 0. Okay? So if I start at this corner, I start at point A. If I start at point A and I go in a counterclockwise direction and end up at point A, let's see if we count the voltages and see if they add up. So I start at point A, I encounter a negative 8.94 volts. I write that down. Now I'm on this side of the resistor. On this side of the resistor, now I have to go down. When I go down, what's the first polarity I encounter? Negative. Negative how much? 4.38. So I'm going to add negative 4.38. Now I'm at the bottom of the resistor. Now I have to continue on my counterclockwise movement. I go to point B. There's nothing that happens between this corner and point B because there's no component. At point B, now I have to go back up to point A. So here, what polarity do I see first? Positive. Positive how much? I see positive 13.32 volts. So I write down, add 13.32 volts positive. When I add these three voltages together, I end up with a 0. Kirchhoff's happy. Same thing occurs here. In this loop, if I were to start at point A and I go in a counterclockwise direction in this right-hand loop, I encounter a negative 13.32 and I write that down here. And then I encounter a negative 10.28, I write that down here. Then I encounter a positive 28, I write that here. Then on my way back to A, I encounter a negative 4.40, I write that down. Add all this up, guess what? I end up with 0. Kirchhoff's happy. There's one more loop. There's a big loop going around the outside, my outside loop. So if I do the numbers on my outside loop, check this out. I think I have it right here. Let's see if my finger moves out of the way. Yeah. So I start at point A and I go here in this direction. I start off and I encounter a negative 8.94, a negative 4.38, and then a negative 10.28, positive 28, and then a negative 4.40. I write these numbers down, I add them up, I end up with 0. So each one of these closed loops, if I start at a point and go completely around and end up at that same point again, if my polarities were right, if the polarities were right, and my voltage calculations were right, algebraically everything must add to 0. That is your double check on any circuit analysis that you do. And that's the power of Kirchhoff's voltage law, my friends. So taking everything that we've done here, here, and here, now we go to superposition. These happen to be equal. Well, and magnify this. And so with superposition, you start off with a circuit, and the circuit goes to show two different voltage sources. They're not in series, so you cannot apply series voltage, series opposing, or series aiding, because they're on opposite sides of the circuit. So there is a very simple way that you do this. Given two voltage sources, you will replace voltage source 1 with a what? A wire, and then solve for all voltages and currents. So when I take this guy and I take this guy out and put a wire in its place, what it is that I have, let's see if I can move this back to here. What it is that I have, give you something a little more, yeah, here it is. It's replaced with a wire. So if my eyeball is here looking at the circuit, my eyeball has to be here opposite the voltage source. I see there's a very interesting relationship between R1 and 2. They happen to be what? Speak up, I can't hear you.
Parallel.
Parallel. So that I can draw this as a simple equivalent circuit. And as if I draw this as a simple equivalent circuit, my REQ1 shows R1 parallel to R2. Now, is this simple to find in RT?
Yes.
Yeah, my 10 ohms plus the 30 ohms gives me 40 ohms. So I end up with a very simple final circuit. And my final circuit is 40 ohms and 8 volts. So have I done my circuit reduction as I've done in previous examples with redraws, taking this, following these steps down to here? Once I get here, can I analyze for I total? Yep.
Yes.
And as I analyze for I total, I determine it's 200 milliamps. Once I determine this is 200 milliamps, this circuit is solved. And now I have to take everything I learned from here and apply it to this one here. That 200 milliamps flows in this circuit also. But guess what? That 200 milliamps flows through an original R3. Which direction is it flowing through R3? Well, this is negative. It's flowing up and to the left. So is the direction of current through R3 clear?
Yes.
200 milliamps and it's flowing to the left. Then it splits. Then I take that 200 milliamps and bring it up here. Then it splits at point A between these two guys. Well, if I got 200 milliamps flowing into this node and it splits between 20 ohms and 20 ohms, each one of those is going to get 100 milliamps each. I'll get 100 milliamps here and 100 milliamps here. That will allow me to do this next step. The next step is to draw my VIR chart. My direction of R3 is to the left, it's 200 milliamps. I can then work out here, 200 milliamps, 200, splits into 100 and 100. These voltage calculations are not necessary, so you can ignore these for now. But what's very important is the direction of R1. The direction of current through R1 is to the left. Did I draw for R1, 100 milliamps going to the left? Yeah. The direction through R2 is from top to bottom, 100 milliamps. Did I draw an arrow for R2 going down 100 milliamps? Yes. So all I need for part 1 of superposition is to do just these 6 cells. That's all I need. Then step 2 says, I'm going to replace VS2 with a wire, bring back VS1, and solve for everything again, creating another chart. And when I go to do this, if I do this, here we go. Bring back VS1, replace VS2 with a wire, solve from this direction, becomes an REQ of 12 ohms. Our 12 ohms plus the 20 gives me our total of 32. 10 volts into 32 gives me 312.15.5 milliamps. I take this 312.5 milliamps, I move it up here. I now have 312.5 milliamps flowing through this circuit. Guess what? That current flows through one of the original resistors, R1 right here. Which direction through R1? To the left. That 312.5 milliamps flows down from the source and splits here. And which way through R2? It's going up. Previously, we had it coming down. Which direction through R3? To the left. So that allows me to do my second, I'll do the current analysis, and allows me to build my second chart. So my second chart goes to show the directions of currents and the values of currents. So I've completed step 1, completed step 2. What is step 3 according to my direction? Step 3 is I have to algebraically add these currents. Well, guess what? Current through R1 is going what direction? To the left. Current through R1 up here is going to the left. If they're both going in the same direction, my final direction for R1 is to the left, and I add these two numbers. 100 plus 312 gives me what? 412 and change, yes? Look at my current through R2 though. My R2 current is 100 milliamps going down, but in my second redraw, I have 187.5 going up. Are they fighting each other? You betcha they are. Which one's going to win? The bigger one. Might is right. Remember that. Might is right. So the 187.5 will swamp out the 100. So 187 minus the 100 milliamps will leave me with a net of 87. And the stronger direction is what? Going up. So in the final analysis, when I do my last chart, this is what I have. 100 plus 312 gives me my 412. My 187 subtract my 100 leaves me with 87, current going up. My 200 milliamps, which goes to the left, is added with the 125 that goes to the left, giving me a total of 325. These are my final directions. These are my final values. These are my final voltages calculated using Ohm's law. Once I know all of this, I can finish this up on my original schematic, which I've redrawn here, write in these values right here. So these are my final values. The final value and direction of R1 voltage, current moves to the left of 8.25. Current through R3 to the left of 9.75. Current going up of 1.75. Now I'm going to use Kirchhoff to prove all of this. Did I label this point W, A, Z, Y, B, X? My first loop, what's it say? A, B, X, W, A. So A, B, X, W, A. I'm making a loop. And in this loop, first thing I encounter is a positive 1.75. I encounter a negative 10, a positive 8.25. I put all those numbers together, I add, what do I get? 0. Kirchhoff happy? Kirchhoff very happy. I do my second loop and I label my second loop A, Z, Y, B, A. So A, Z, Y, B, A. Positive 9.75, negative 8, negative 1.75. Add these up, guess what? 0. Kirchhoff's happy. My final loop is the big one all the way around. And the big one all the way around, W, A, Z, blah, 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 blah. If I go all the way around, guess what? Add them up, they all add up to 0. So the end result of the exercise that you're supposed to turn in, and some of you have turned this in already, this document that I'm holding in my hands, the final result that you have to come up with, this drawing at the bottom of the paper, is this summary drawing that's in here at the end of superposition. You have to specify the final polarities. You have to specify the final directions of the arrows. You have to specify the final values of voltages. And you prove it to yourself by using Kirchhoff's voltage law, by making sure each of those loops adds up to 0. That is your superposition, and some people turned it in already, some of you have not, but that is the short version. You'll have to look at all the videos that I've posted and over again, and then you'll be able to generate this output, and there's your final answer right there. Okay? Okay. So any questions on superposition? We are out of time. But if there are questions that arise, you know you can always reach me through Canvas, inquire through Canvas, and I'll be happy to answer those questions for you. Okay, guys?
Okay.
All right, so you know about your soldering exercise, you know what's in front of you, you know where you're going to be Tuesday, and the procedure for Tuesday. So everything is good, good, good. I'm very happy with all of this. And we will see you in Canvas, and we'll also see you next week, okay? So with that, thank you very much for being a really good crew. I'm proud of you guys. Good job. Take care now. Adios.